Hi, my name is Sylvain Allais, and it is my pleasure to present our contribution to CAV 2021 called Foundations of Fine-Grained Explainability, a work that was done with my colleague Hugo Tremblay from Université du Québec à Chicoutimi in Canada. Before diving into the subject of our paper, please allow me to start with a short and funny introduction. Imagine the office of a private detective late at night, when suddenly a stranger slips an envelope under the door and leaves. The message it contains says that a crime has been committed and asks the detective to try to find the person responsible for it. Our detective has no choice but to start walking around the city and follow the trail of evidence. One clue leads to the next, and so on until the detective successfully corners the criminal and delivers him to the authorities. This looks like the summary of a police movie, but our use of information systems of various kinds sometimes look like such a kind of investigation. In a typical situation, we give to a system what we call inputs, sometimes lots of inputs, and then some magic happens, and we get from that system, well, outputs. But how can we link the ins to the outs? In other words, if someone points to you a piece of the output, can you retrace the pieces of the inputs that are responsible for it and explain why? This is a difficult task, especially if the system that turned the ins into the outs is large and complex. You may sometimes hear the terms explainability or traceability or lineage. They actually mean different things, but in this work we shall conflate them into the capacity to link outputs of an information system to its inputs in a meaningful way. In a nutshell, our work is to provide a formal definition of what it means for an input to explain an output for an arbitrary information system that we consider as a black box. We shall see that one particular feature of our formal model is the fact that it is fine-grained. Our detective story would not be very interesting if by the end of the movie, all we knew was that one of these guys perpetrated one out of a list of many crimes. What we expect from our detective is to come up with a more precise answer, pick one of the crimes, and identify the person who is responsible for it. The same applies for an information system. Knowing that the whole output produced by the system is somewhat explained by the whole input given to it is not very instructive. Better yet would be to identify an element that forms the output and retrace it to an element of the input, the same way that our detective selected one crime in the list and associated it to one person in a group of suspects. A consequence of this observation is that our model must acknowledge the fact that the inputs and outputs produced by a system in the real world are seldom simple atomic objects such as numbers or letters. By and large, they are themselves composed of finer elements, and we must be able to refer to them or point to them. So before even defining how to explain outputs from inputs, we need to take a step back and clarify what it means to be part of an object. First, we define a set of objects U that is partitioned into subsets O1, O2, O3, we shall call object types. We don't care what these types represent, but you may, for example, imagine the set of all Boolean values or the set of all numbers or character strings or lists, etc. We define a special symbol, the square box you see here, to represent a particular object which is nothing. To simplify things, we assume that this nothing belongs to every object type. Each object type is associated with a set of functions we call its parts. Given an object of type O, a part pi returns another object which may be of another type O prime. Intuitively, we expect this return value to represent some element that composes the original object. Of course, a part must be such that if passed the special object nothing, produces nothing in return. We assume that two special parts exist for any object type. The first is denoted by the symbol 1 and corresponds to the identity function, while the second is denoted by the symbol 0 and corresponds to the function that always returns nothing. In other words, 1 is the part that encompasses all of an object, while 0 is the part that refers to nothing of an object. We call an object type a scalar if the only parts that are defined for it are 0 and 1. Any other object is called composite. By the way, nothing prevents a part of an object from itself having parts. That is, objects can be nested within each other, and consequently, parts can also be composed. In the illustration you see here, we have two abstract composite objects, x and y, of the same type, represented by the large gray rectangles. There are three parts that are defined for this type, labeled pi a, pi b, and pi c. We see that what is returned by pi a is itself another object of composite type, having parts pi 1 to pi 4. Objects of a given type do not need to have the exact same structure. It is okay for a part to return something for some objects and nothing for some others. Take the example of part pi c. It returns the yellow rectangle labeled 7 on object y, but it returns nothing on object x. Part composition operates in the usual way. If I apply pi 1 composed with pi a to object x, I refer to the part pi 1 inside the object that corresponds to part pi a inside object x, which is nothing here but the rectangle 8 in the illustration. This way, it is possible to refer to parts of objects and parts of objects, and so on. We say that two objects, x and y, differ on some part pi if applying the function to each of them returns two different objects. Before moving on, we need one last notion that will enable us to make comparisons between parts. Given a part pi, we say that a composition pi prime circle pi is a refinement of pi, and conversely, pi is said to be a generalization of pi prime circle pi. The intuition behind these two dual concepts is simple. If a part pi extracts something out of an object, then composing it with another part pi prime will extract a quote-unquote smaller part of that object. This is what we mean by refinement. All these concepts can be extended to sets of parts in a relatively straightforward way, and here, due to lack of time, I will have to skip these relatively uninteresting technical details. This little detour to define terminology about object parts is arguably a bit abstract, but it gives us a general yet precisely defined concept upon which the notion of explanation can then be defined. Just to make things more concrete, let us examine a few simple object types and what parts could be for each of them. First, we have common scalar types, such as numbers or Boolean values that have only 0 and 1 as their parts. Then let us nest these scalars into an ordered structure, such as a list, whose parts could be each element of the list, probably. Note here the bracket notation that we shall use for the rest of this presentation. So number n between brackets designates the nth element of a list. So I'll stop here. This is already enough to cover the data structure one gets in a programming language such as Lisp, so it's probably good enough to start with. Okay, at last, we can now go back to our main concern, which is to attempt to define a part of the output and try to find what is the part of the inputs that are linked to it. We make very few assumptions about what the system we consider can be. All we know is that it is an unknown black box that receives an input of some type O and produces an output of some other type O prime. So in the following, I shall refer to this thing as a function because in theory, that's exactly what it is. I think the best way to understand where our definition comes from is to consider a simple example. So here's an extremely simple example. A function that takes as input a list of two numbers that I will call x and y and returns their product. Simple, but as you will see, encompasses everything we need to consider. If I evaluate this function with x equals 1 and y equals 2, I get as an answer 1. I thank you. Now, if I ask you the question, why did you get this result? Can you point to something in the input I gave to the function that is sufficient to explain the result? If you think about this for a few seconds, you might answer that, well, both x and y are involved in the result, because if you change any of these two values, you will get a different result. If I change x for 2, I get 4, not 2. And if I change y for 6, I get 6, not 2. So in a way, the two elements of the input are important. Okay, then let's try with other inputs. Say x equals 1 and y equals 0. I know you know that we get 0 as a result, and I ask you the same question as before. Can you point to something in the input that explains the result? This time you should come up with a different answer. We all learned in elementary school that 0 multiplied by anything is equal to 0. The key word here is anything. It does not matter what the other number is. As soon as there is a 0, you get 0. So does the value of x matter here? No. Knowing that y equals 0 is all you need to know to understand the return value of the function. Do anything to x, it changes nothing to the result you get. Okay, one last example, and you probably see me coming here. Suppose both x and y are 0. We still get 0, but what happens to my question? Sure, saying that x is null is sufficient to explain the result. But then saying that y is null is also sufficient. As a matter of fact, changing a single one of these values still has no effect on the output we obtain. Therefore, our explanation this time should evoke an alternative. Either of the values explain the result. This example was simple. Now, the harder part is to come up with a general definition which, for this example, would behave as we expect. So here it is. Actually, this is the text of definition 1 in our paper, and as a matter of fact, this is the only definition in the whole paper. So, let us go back to our simple function and check if it indeed behaves as we expect. So with x equals 1 and y equals 0, what is an explanation? Well, x is an explanation as it is possible to change only this value and get a different result. Y is also an explanation for the same reason. If we were to illustrate this graphically, we could draw something that looks like a tree where we state that x and y are each an explanation, as you see here. Second example with x equals 1 and y equals 0. This time changing the value of x does not produce a change in the output, so x is not an explanation, only y is. But wait, if changing y produces a different output, then obviously changing both x and y may also produce a different output. So why do we consider only y? This is where an important part of the definition kicks in. For something to count as an explanation, no refinement must also satisfy the definition. So altering both x and y indeed produce a different result, but altering only y suffices. So y is an explanation. The same cannot be said of x alone, so x is not an explanation. Finally, with x equals 0 and y equals 0, we have seen that either of them suffices to explain the result. So they should both appear, but as alternatives. Indeed, changing x alone has no effect. The same for changing y alone, so both need to be changed to produce an output, a different output, which is the dual to saying that either of them suffices to explain the result. This is why the only part that fits our definition is the one including both x and y. In other words, a set made of multiple parts maps to a disjunction, while multiple sets of parts map to a conjunction. Honestly, if you followed me this far in the presentation, you understand everything that counts. The rest is just a matter of turning the crank and extrapolating the consequences of what we just learned together. So just for fun, let's take a more complex function, which takes as input a list of numbers and produces as its output another list made of the product of each triplet of successive numbers. So for this list here, you would get this one. Let's take the first element of the output list and ask what explains it using our definition. So what parts of the input are sufficient to get a different value at that position in the output? It is easy to see that the first three elements of the input list are all sufficient to produce a different value, so they each explain the output. Now let's focus on the third element of that list. Why is it null? Obviously because element at position 4 in the input is null and nothing else. So all these answers are exactly what you get if you apply the definition of explanation. Therefore, it appears that our definition matches one possible intuitive way of explaining a result or part of a result. Concretely, however, it is not realistic to think one would apply this reasoning manually for every conceivable function, and especially functions with more complex inputs or performing a more complex computation than the simple examples we've seen. So what can we do? Well, here we can take advantage of the fact that complex functions can often be defined as the composition of more elementary functions. In other words, the output of one function is given as the input of another one to form what resembles a graph or circuit of computations. Then, if we establish in advance the possible input-output relationships of each function, it becomes possible to construct the explanation of the whole by simply joining together these pieces of explanation. It is working the pipeline, but in reverse. We ask the explanation of the output of the last function, which will link this output to parts of its inputs, but then these inputs, the input parts, are nothing but output parts of the function that came before, and we restart the process. So are we sure to get the right result in doing so? No. But a theorem in the paper states that if each function individually produces a generalization of its explanation, what you obtain for the whole circuit is also a generalization of its explanation. That is, everything that does explain the result is there. This may seem blurry, but in reality, at least for the examples we studied, what we get is the exact explanation we expect. To illustrate the approach, in the paper we formally define the explanation of an output part for a small set of elementary functions on scalars and vectors, which are illustrated here. We have Boolean connectives, basic arithmetic, operations on vectors, such as applying a function to each element, extracting an element at a given position, or even evaluating a function on a sliding window of elements. There are also a few functions for manipulating strings, which are handled as lists of characters, more or less. This may not look like a lot, but nevertheless, it represents a non-trivial fragment of a functional programming language such as Lisp. In addition, we also implemented these concepts in the form of an open source library called Petit Pousset. Petit Pousset is written in Java, and it exposes elementary functions as descendants of function objects that can be instantiated and connected to form complex function circuits. When evaluated, a circuit produces both its return value and another special object called a queryable, which contains information related to the explanation of the function's result. As its name implies, the queryable can be, queried. We can pass to it an object that designates a part of the output, and the queryable will produce in return a graph, linking this part all the way up to the ultimate inputs of the whole circuit. The circuit you see here is composition of 5 elementary functions. I don't have the time to explain it to you in detail. Taken as a whole, it checks that the sliding window average of the second element of each text line in a file is always greater than 3. If we evaluate this function on the following text file you see here, the output we get is the single value false. But if we ask the queryable for the graph corresponding to this result, what we obtain is an explanation of the result. We can see 3 alternative explanations for this result, each involving 3 lines of the input file, or more precisely, 3 specific substrings of each input line. These locations correspond to the numerical parts inside each line, and only those lines involved in a faulty window, whose average is less than 3, are present. And this is the link to computer verification. Because if you see this thing as a test oracle for some weird condition, then what you have here is a test oracle that explains a failure. It does not just tell you that there is one. Note that all this is generated automatically by Petit Pousset. A user simply needs to create the circuit and evaluate it. The generation of the explanation is then achieved through a single line of code. And that's it. Of course, I had to gloss over a few technical details that you can find in the paper, but the essence of our contribution is that. What's even more interesting is what lies ahead, now that we have these simple formal foundations. I have a couple minutes left to tell you about some exciting research directions. First, some mileage can be done by simply studying the explanation graphs themselves produced by a function. For example, take a look at the graph here. You will notice that some text lines seem to be more important than others by being involved in all possible explanations, as is the case for the leaf node designating line 5 at the center. It turns out that this line has a large negative value, minus 80, causing all the windows that contain it to fail the condition. So this last observation would not be possible in a structure that does not keep multiple alternate explanations. So not only are some parts of an input responsible for the output, some of them may be more responsible than others. So this could be used as the basis for a quantification of this notion of responsibility. We could ask ourselves other questions, such as, is there a part of the input that never explains the output? This could form the basis of an alternate definition of an existing concept that is called vacuity. Are there functions that produce more distinct graphs than others? And if so, what does it tell us about these functions? Also note that our definition of explanation is dependent on what we define as the parts of various object types. The parts that we considered in the examples are arguably intuitive, and the behavior of explanation based on these parts produces results that match our intuition. However, nothing prevents us from defining parts of an object type in a completely wacky way and then examine the consequences of these definitions percolating through the rest of the formal model. For instance, who said that numbers had to be scalar? Why not define parts of a number as its first, second, third, etc. prime factors? Then a function that returns true or false, whether a number is even or not, could point to the first prime factor of the number as the sole part that explains the result, and not the number as a whole. So you get the idea here. So thank you very much for your attention. I hope this talk has properly conveyed the notion of explainability, but even more so encourage you to work on this topic. Goodbye.